这个吗？肯定是这个，这个一般不买，这个一般买。是这个，这个是4，还是5？不想读了，也好烦。拍照片，拍照片。我今天下午去把那个表格拿来了，就是134号。差不多吧。我在看申请。他说就是不需要面签，就把资料交上去，然后我们再做一个在上面把那个检查身体和入职。可以。就是这个。就是这个周里的附近的体检中心。还要进洗澡。让他们早点，我看那个飞机票贵要死了，我还要。真的，1万2，而且还转，你知道吗？哦。我去看看。我只给他们买了，我才能买。你给他买了，你不应该我干什么鬼？不能啥这些。那你也得和他一天不走，就是他都让我等，反正他的票价就是因为我不定。你就等最后2天吧，说那5万的事，就是那个，但也不一定。不是要看个什么？要看作业的。看我这马上就把别的再钻研。我要去把作业打出来，太恶心了。你给我打的那个我不知道丢哪儿了。你上3，给我打的那个我不知道丢哪儿了。下一步就，我们在下一步就是在27号，但我就
If they swap, right? How's the homework going? Easy? You need another day on the homework. No?
Yes. Can you repeat the question?
You need another day
Yeah, maybe.
on the homework.
Maybe you can talk about homework this class because the second talk is a little hard.
So what are you saying, yes or no?
Yes.
Yes or no? Approve? And you?
Yes.
You should say sí. Yo hablo español. Yo know English. Yo know hablo English. You know what that means? I don't speak English. So I'm gonna give you until Wednesday on the homework. Okay? Wednesday. That'll be 14. We talked about this problem last time. It was the RC, the circuit problem. X of t input. We'll make that a current source. Current source as X of t is stochastic. It's a random process. maybe the telegraph signal. And so we have the voltage at this point, y of t, is c times dy. This is a random variable, this lowercase. Oh, I might as well make it cap. dy dt plus gy, conductance G, and this capacitance C. It's equal to the input current source, X of t. We'll say the mean of X is 0. The mean value. Mu X is equal to 0. And we are given, for example, the autocorrelation function R X. Since we'll be talking about cross correlation, cross X with Y, X of t and Y of t. So the cross correlation R XY of T1, T2 is equal to the expected value of the random variable X at T1 times the random variable Y at T2. Cross correlation. Autocorrelation. Autocorrelation is RX, X, T1, T2, which we call RX, the autocorrelation function. But you can use double subscripts or single. Expected value of X at T1 times X at T2. So that gives the cross correlation. A lot of times we're given information, only information about X. Could be maybe its mean value and its autocorrelation. That would be the only information that you would have. Information given. Mu of X and R of X, T1, T2. If these are wide sense, or if these are wide sense stationary, then the expected value of X would be independent of time, meaning it would be just a constant. So if I want to find then the expected value of y, I would go to this differential equation and take the expected value, that is the capacitance, times the expected value of dy dt plus v plus g, the conductance, times the expected value of y would equal to the expected value of the input. The input at time t. And if you make the expected value, let's say mu x, we'll say is equal to 0 as a zero mean. For example, if you look at the telegraph signal, it has a zero mean between 1 and -1. It doesn't have a zero mean if the telegraph signal goes between 1 and 0. But if it goes between 1 and -1, it would be 0 mean value. The random phase signal, x of t equals cosine of omega t plus theta. If theta varies over a range of 2 pi, if the probability mass function varies between minus pi and plus pi, then its mean value would be 0. If theta varies between 0 and 2 pi, its mean value is 0. If it's defined over any 2 pi range, its mean value is 0. If it is defined only between 0 and pi, its mean value is not 0, and it would not be wide sense stationary because the mean value would depend on time. So WSS means that mu of x is equal to a constant. And for the sake of simplicity, make that constant 0. So, the expected value of dy dt of dy dt is equal to the integral. I'll use an integral. It could be a sum, doesn't have to be an integral. We need the mass density of something of y. It would be Fy of y dy dt times dy would give you the expected value, right? But we're integrating on y, not t. So we could take this function here and say that is d dt of y, Fy of y dy. What is this? It's the mean value of y, mu y. If it is wide sense stationary, Is it a function of time? No. And so therefore the derivative with respect to time would be 0. So we have then, this would be equal to 0. Expected value of y could be 0, or it could be a constant. If it is Whiteson stationary, it's a constant or constant or 0. Now, if the expected value of x is 0, then the expected value of y is 0 in this case. Doesn't matter how many derivatives you have at this point. All of the derivatives with respect to time would be 0. And the only one left would be this term here. And so g times the expected value of y would equal to the expected value of the input of the random variable x. So that takes care of the expected value of y. So it turns out to be 0. Well, what about the other equation that relates to how do we find, as we're interested in WSS, autocorrelation, cross-correlation, these are the things to worry about. Only these things are important in this problem. And so I go back to the differential equation. So cross-correlation and correlation talk about T1 and T2, don't they? And if it is Whiteson stationary, T1, the autocorrelation function will always be dependent upon T2 minus T1, or the absolute value of T2 minus T1. So if I look at that differential equation, I could write it as C dy T1 dt1. Right, T1, T is equal to T1, plus the conductance Y at T1. T1 is equal to X at T1. Now let's talk about multiplying this whole thing by X of T2. And so I would say C dy, y is a function only of T1. dt1 times X of T2 plus G y of T1 X of T2 equals to X at T1 times X at T2. So now we take the expected value of this expression. What would be the expected value of this? It's the autocorrelation. So expected value equals expected value. And this expected value is Rx, Rxx, T1, T2, the autocorrelation function. White and stationary, it only depends on the difference, T1 minus T2, absolute value of T1 minus T2. And so this first term, the expected value, well, this is a constant to capacitance. Expected value of dy T1 dt1, not dt2, not dt, dt1, times x at t2. Again, the dt1 we can take out of the expected value. And so this is C. dt1 times the expected value of y at t1 times x at t2. And what is that? That's the cross correlation between x and y. So this is C. dt1r, I'll say x, y, t1, and t2. So we now have a differential equation because I know what this one is, right? It's the same cross correlation. So we have C dt1 times r. I'm going to just write shorthand for x, y. We know what the variables are, t1 and t2, plus g times r x, y is equal to, the autocorrelation function, Rxx. And that's T1, T2. Can we solve that differential equation? Let's see. What would you like to take for Rxx? Would you like an impulse? An impulse? That makes life easy, doesn't it? Assume Rxx of T1, T2 is equal to delta T1 minus T2. That's an impulse. If I'm going to solve this differential equation, I can do it with Laplace transform. So I'd take the transform of the variables, Laplace transform. What is the Laplace transform of that? Okay, Laplace Laplace transform of dt1 Rx y t1 t2. Well, mathematically, that's equal to the integral from 0 to infinity of dt1 Rxy t1 t2 e to the minus s. Here's where you need to be careful. This is s t1 dt1. We're taking the Laplace transform with respect to the t1 time, not t2 time. Because our differential equation is defined in terms of t1. Call it t or whatever. So what is the Laplace transform of a derivative? It's zero to infinity of the derivative dt1 t1 t2 minus s t1 dt1. That's equal to s. I think it's s times the integral from 0 to infinity of Rxy t1 t2 e to the minus st1 dt1. Is there an usually there's an initial value to worry about. We'll say Rxy at 0 t2 is equal to 0. That's how we got this. Otherwise, you'd have to have a minus sign here at the initial value. Did you do Laplace transforms? Right. That's everyday information for electrical engineering. Okay, so what am I going to call this transform? I'll tell you what I'll call it. I'll say it's equal to S. I put a curly bracket. Curly bracket X, Y, S, T2. Usually you write a capital F for the transform of a lower f of t. Capital F, the transform, lower f, the time function. But I've already got a capital R. I guess I could go to lowercase r, go in the opposite direction. So that means that we have C, S, R, X, Y, S, T2 plus G, R, X, Y, S, T2 ST2 is equal to RXX. Yeah, here we had an impulse. So that would be equal to R XX bar, curly bar, oh, curly bar, curly bar. Curly bar, this would be S T2. ST2. Okay, let's see if we can find the RXX curly bar ST2 is going to be equal to integral from 0 to infinity. And we know that the this thing here delta T1 minus T2 e to the minus S T1 dt1. Oh, that looks rather formidable, doesn't it? Shall we see if we can we integrate this? Who cannot integrate it? Okay, then integrate it. Do you think this is equal to e to the minus st2? What do you think? I know if you just had delta T1 minus T2, that'd be easy to integrate. On the integration here. Typically, we write the integral of delta t minus t0 g of t is equal to g of t0, the so-called sample. That delta samples the function. But the integral from a to b has to include t0. Integral from a to b has to be a t0 there. And it's equal to g of t0, but if t0 is not in that interval, then it's 0. So it's this if T0 is in AB, the interval AB. Otherwise, nada. But what about if we put absolute values there, T minus T0? Well, you know, I've thought about that problem. And this is the way to look at it. I'm going to say delta sigma of T minus T0 is equal e to the minus T minus T0 squared divided by 2 sigma squared, and in the denominator 2 pi sigma squared. That's that old normal distribution. Now, as sigma goes to 0, this thing shrinks and looks like an impulse because we know the total area is 1. And so I'm looking out at T0 and I see this impulse there, delta sigma, T minus T0. See it? See it there? Sigma goes to delta sigma, T minus T0 goes to T minus T0 as sigma goes to 0. So it's just a matter of whether you want to take the integral of the limit or the limit of the integral. Either one. I think that mathematically it's okay. Or mathematicians might not like it. That's where they like to worry about countable sets. They call that Lebesgue, L-E-B-U-G-E, Lebesgue integration. We just, as engineers, we just do Stieltjes integral. So I conclude that the integral of delta of T minus T0, absolute value, G of T, dt. I'm going to put a sigma there. And here's my G of, or here's my delta, and then here's my G function. Now, as this sigma gets smaller and smaller, this thing squeezes up, doesn't it? So I could approximate this as G of T0, the integral T minus T0 dt. Because this thing, the value of G at T0 is the dominant part of this. The thing shrinks and shrinks. So that's why I write this as that. Now, the question is, what is this integral? Okay, let's say t is less than t0. So this will be the integral from a to t0. And that would be delta sigma. T is less than t0, so it's t0 minus t dt, plus the integral of t0 to b, t minus t0 dt. And so we're integrating this, and this argument is negative. That is, t is less than t0. Well, if you're getting close and t is in that point, it looks like this value here is the same as that value. And so when we integrate to t0, what do we get? Half the area. Right. So when you're integrating, you're talking about that area as one area, and you're talking about this area as another area. But it's always a half. So it's a half plus a half. F of t0. That's a long-winded discussion. Meanwhile, a to b delta t minus t0 g of t dt is equal to g of t0. Okay. So what do we have? The Laplace transform of t minus. We want the Laplace transform. It looks like, so this thing picks out t1, this thing pops up at t2, so it picks out. We're integrating on t1, this thing peaks at t2, so you just samples, get t2. So we are left with CS plus G times RXY ST2 curly bracket is equal to minus ST2. All of that work just to get to that. And so RXY curly bracket ST2 equals 2 e to the minus ST2 divided by C times S plus G over C. You know what G over C is? Isn't that a time constant? RC time constant. G is 1 over R. So it'd be RC time constant. RC time constant. By the way, what kind of filter is that? Is that low pass or high pass? Huh? I think it's low pass, don't you? Right, because at high frequency, C is 0 and no voltage. The current just goes through, it doesn't create a voltage at that node. When the frequency is 0, it creates a big voltage, so all the current goes through G, which means it produces a voltage. So this is low pass filter. Low pass filter, low pass. H of F is 1 over F plus R 1 over time, 1 over RC. That'd be F0. Oh, F0 is 1 over the time constant. Oh, so F0 is equal RC. And so here's looks something like that. H of F. H squared of F is 1 over F plus F0 quantity squared. Transfer function. H is the transfer function for that network. So we're sitting there. And so now Rxy of T1 comma T2 is the Laplace transform minus 1 e to the minus S T2 over C times. Let's take out 1 over C. So it'll be S plus 1 over RC, time constant. The inverse Laplace transform of that. I hope we got this computer working. You know, the homework problem that you have, It's not much different from this, except you would have two poles in the denominator because it's second order differential equation. You can assume that the initial conditions are zero. Did you know Mathematica is your friend? I think this is coming alive. 1 over C. New document. Give it a little life. 300%. Make the screen legible. And I'm going to say inverse. LAPLAs. Oh, it's already asking me if I want the inverse Laplace transform. Now I'm going to say EXP of minus S T sub, okay, T sub 2, ST sub 2. And I want to divide that by what? Control slash. And what we have S plus 1 slash RC. It's too bad we can't call. There it is, RC. Now we got to tell it what the transform variables are. Well, they are S and T sub 1. There it is. That assumes T1 is greater than T2. You know what Heaviside theta is? It's a unit step. Let's say RC is 1. T1 has to be greater than T2. because Heaviside theta doesn't exist. It's 0 for T2 greater than T1. If you want to, you can say T1 is tau, right? T1 minus T2. So plot. Yeah. Oh, let's plot. Let's plot that. Okay, so from we're going to plot that with respect to T1. Control underscore T1. We're going to let T1 vary from, you can say minus infinity to plus infinity. I don't know if this is going to work. We'll see. No, it's not going to work. RXY T1 T2. RXY T1 T2 is equal to with the 1 over C e to the minus e to the minus T1 minus T2 over RC times the unit step T1 minus T2. And so here is T2, and there's, looks like that. That's it. This is R, the cross correlation, T1, T2, T1. Or you could say it is tau. Looks like that. So it's just one side. Okay, what about RYY? RYY. Okay, we had C d squared, or shoot, dy at T1 dt1 plus g y at T1 is equal to x at T1. And now I'm going to multiply by y of T2. So we have dt of r y T1 T2 plus g RYY T1 T2 as equal to RXY T1 T2. So we have another differential equation to solve. And so we take the Laplace transform again. You know, we already have the Laplace transform of that because that's what we started with. See, here's our xy. RXY. So we go about the Laplace transform. We have C. We have C, S, R, Y, Y of ST2. I've got to put a curly over it now because we took the transform. Plus G, R, Y, Y of ST2. And that's equal to RXY curly T1, T2. And that's that. So we have C times we have CS plus G times RYY curly bracket ST2, and that happens to be equal to this thing here, 1 over C, e to the minus T1 minus T2 over RC times the unit step T1 minus T2. It looks like R, Y, Y, curly S, T2 is equal 1 over C. Oh, I beg your pardon here. I beg your pardon. This is equal to, I beg your pardon. It's equal e to the minus 1 over C, e to the minus ST2 over S plus 1 over RC. And so what we find that this is equal to 1 divided by C, pick out another C squared. Oh, there's another C squared, and this is e to the minus ST2. Look at this, S plus 1 over RC, quantity squared. Isn't that something? So, RYY T1, T2 is the inverse Laplace transform of that. And that turns out to be, look. Oh, I left off the 1 over C, didn't I? So I'm going to put 1. I'm going to put 1 over C squared. That's a capacitance, C squared. And now all we do here, look how simple this is. And so I'm going to put caret squared. Cross your finger. There it is. Almost the same thing, except you got a T1 minus T2 there. RYY, T1, T2. Okay, you have that, and then you have to multiply that by a line. And so it does this. There's RYY. Can you do the homework now? Huh? Now, the only difference here is we had a first order equation. You're going to have a second order equation to solve. We have 10 minutes before we tie the knot. We have 10 more minutes. That's all the time we've got. We did expected values. Expected values are ensemble averages. Expected values are ensemble average. That is, you average over a probability density. Right. Expected value. Expected value of x of t is equal mu of x. A time average x of t, we'll say t zeta. Zeta is the random variable. X of t zeta is equal to 1 over 2, the time average, 1 over 2 times cap t, integral from minus t to plus t of x of t zeta dt. That's a time average. Ensemble average mu x t equals to 1 over n. can be a function of time. Summation of I equals 1 to n x of t zeta I. That's a ensemble average. You know, as capital N goes to infinity, remember we talked about the sum of this right here. What counts events, doesn't it? An event counter. Every time an event occurs, if we define x of t equal to 1 for a success in the random variable zeta, then, and it's 0 for a failure, then this counts the number of successes. Counting. So divide by n. We talked about Sn is 1 over n summation. This is capital N. I equals 1 to capital N of zeta I. Remember, that was the counting successes. Zeta sub I is 1. See, here's the random variable. If we throw a 1, 2, or 3, zeta is 1. If we throw 4, 5, and 6, then zeta is 0. 1 plus 1, no, plus 0, plus 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. We counted 11 successes, and I threw that 22 times. That's called the ensemble average. Okay. The probability that the limit as n goes to infinity of 1 over n summation I is 1 to n of zeta I is equal to mu of zeta is equal to 1. Ergodic. Do we know ergodic? What does ergodic mean? ergo, ergodic process. I think next time we're going to go into Einstein. Wiener. K-H-I-N. Kenshin. C-H-I-N. Have you ever heard of this Wiener-Kenshin theorem? Anybody? You heard of it. Okay, I'll tell you in the last minute. It says the Fourier transform of the autocorrelation function is the power spectral density. You remember the Willie Sutton power spectral density? That's where the power is. Willie Sutton said he robbed banks because that's where the money is. So homework will be due on Wednesday. All right, that's it. Ciao. Tai Jin.
Question. I have a problem too because I think I can't figure out how to calculate the mean value of the CT.
Well, this thing here, you got, if you multiply this thing through